So what I wanted to do is I'm going to talk about energy a little bit, but the first thing I want to do is I want to talk to you guys about some due dates and some housekeeping information. So tomorrow we have a due date. It's October 4th, and everyone's got a due date regardless of what session you're in, 18, 16, 14, 12. Everyone's got a due date. Everyone's got stuff due. Um, I've gotten some questions about fall break. Regardless of whether you have a fall break or not, everybody has a different schedule at virtual school. That's kind of how virtual school works. At your physical school, you have a different schedule. At our school, everyone has the same schedule, and that is that we do not observe fall break. And so, regardless of what you're doing in your home school, you still have to work every week except for basically Thanksgiving week. We get that one off. But you still have to work through, even if you have a fall break, we don't. So you're more than welcome to work through that stuff early and turn it in early. That way you don't have to worry about it while you're on fall break, or you can just work on it while you're on fall break. But we do not have a fall break at virtual school. And I'm sure you guys saw that when you log into virtual school. Before you log into our course, they had a big announcement about fall break. We talked about fall break in the welcome session. So, it shouldn't be a surprise to you, but I'm still getting a lot of questions about it. So anyway, that's the deal with fall break anyway. So tomorrow on 10/4, I'm just going to talk about the tests that are due for each section. So the 18-week and the 16-week kids have the application of Newton's Law test due tomorrow. Okay, so y'all will need to turn that in by tomorrow to get full credit. And remember, tests are 40% of your grade. So that's why I really focus on what tests are due each week, because that is the bulk of your grade. Not getting a 0 on a test is huge, or getting late credit on a test. Even if you make 100 on a test, if you turn in 3 days late, that's a 70. That you're all the way down to a C. And if you get maybe an 80 on a test, then you get 30% off. That's like a 50. Right? So it's really important to turn in your tests on time. The 14-week students have the Newton's Law test due. And remember, both of these tests have synchronous sessions, these live sessions, the recordings where you can watch the recording and you can get some points back on your test. You can get some extra points for your test. I highly recommend watching the synchronous session reviews before you take the test rather than after. I think they'll be more useful to your grade that way, because then you're getting some review as well. The 12-week kids, remember, you guys are doing 18 weeks worth of stuff in 12 weeks. So you guys actually have your 1D kinematic test and your 2D motion test tomorrow. So that's a lot, right? So if you don't do those two, that's 2 zeros in that 40% category. That's huge. Okay, it's really important to do your tests. Next week, your due date is the 11th. The 18 and the 16-week kids have their mechanical energy test. So today I'm going to kind of review a little bit for energy, and then I'll also review next Tuesday as well. The 14-week kids have their application of Newton's Laws test due. And remember, I also have, if you guys go to those course resource newsletters that I link to in the course, I'll actually I'm going to go ahead and bring that up for you guys when I finish this, just to kind of show you what it looks like, so you guys can see that, and then show you how to kind of get to those, because they're really helpful. and supposedly screen sharing is working now. And then the 12-week kids have their Newton's Law test due next week. So you can see those 12-week kids, I got to hand it to you. You guys are kind of, you truck through the course pretty quick. But, you know, it allowed you 6 extra weeks in the beginning where you guys didn't have to do any physics. So, you know, I guess it evens out. So let me see if I can screen share with you guys. Okay, so now it looks like hopefully you're getting my screen. And so this is kind of what the website should look like for you guys. I'll put it as a student so you can really, okay, here you go. So here's what it looks like for you guys when you log in. Now this right here is the bulletin board. Now the bulletin board is what I've done with that is I've gone ahead and I put links to all your different modules. So example, let's say you're working on the applications of Newton's laws. You know, your test is due tomorrow and you want to see if there's any extra information. Go to this, you can click on the application of Newton's laws right here, and it's going to take you to the course resource newsletter. Okay, it's got stuff for every single assignment for that unit. So for example, if you're having trouble with the coefficient of friction lab, you can click this and I walk you through the video. Here's some prac problems and solutions for this quiz. Here's some concepts that are discussed in this quiz. I discussed them in this video. And then here's some information about elevator problems. And if students ask me questions about different labs or things, I put the questions and answers on here as well. Here's some stuff with systems and slopes, Newton's gravitation law. You can see that I walk you through the video here. Some more information about circular motion, Newton's laws, the test. If you look at the additional resources, you can see here is the review for the new application of Newton's law, the second half. Here are the video walkthroughs for the 2 labs. Here's some really good information about elevator problems. I think it's really helpful. Some stuff about forces. Here's some things from Khan Academy. These videos are other videos that I've made in the past for students, and then little like note templates that go with them. So to kind of keep you focused while you're watching the video, here to solve some problems. So there's just a lot of resources here available to you if you take advantage of it. And there's one of these for every single unit. So whatever you're working on, there is something for you, whatever module you're working on, there is information for you to kind of help you with your different assignments and things like that. And if your question isn't answered, you can always email me and I'll answer it to the best of my ability. So let's see. Let's talk a little bit about work now, kind of switch gears. And so we're going to need this work information to kind of work to do the energy stuff. Okay, so these are our 2 work formulas. We have W equals F times D, and then we have W equals FD cosine theta. And so you're going to use the cosine theta one when you've got something at an angle. And we'll do a practice problem like that in a couple slides. But yeah, the cosine theta is for an angle, and then otherwise you're going to do just F times D. And a big thing with this, and I'm gonna write it on here in case sometimes I watch videos on mute, and so I'm gonna write it here just in case you're watching the video on mute. No work is done if you don't move. Okay, so you can see that both of these formulas have distance in them. Okay, if your distance is 0, your work is going to be zero because 0 times anything is 0. So that's why we say no work is done um, if you don't move. So it doesn't matter how hard you felt like you worked, how much force you used, whatever. Um, so here, oh look, I've already got that. Here, look at me. I'm so on top of my game today. So if nothing moves, no work is done. Um, work is the transfer of energy by applying a force. And see, here I am again. I highlight it in red, and I don't like to use red because I feel like it makes people sad or mad or whatever. I heard that when you grade papers, it like hurts kids' self-esteem if you grade them in red. So I never did that. But anyway, so the transfer of energy by applying a force, causing the object to move. If nothing moves, no work is done. Your work is measured in joules. And the way I remember this, it sounds totally stupid, and my students always laugh at me. But I say that it takes a lot of work in order to be able to afford joules. And so that's how I remember that work is in joules, which I know is silly. But anyway, that's how I remember it. This is the conversion for it, just in case you're curious. But you're not going to have to do that as long as you've got your formulas correct. So your work is equal to force times distance, and you can put it in a triangle if you want to. Force and distance would be on the bottom, and work would be on the top. So let's try and solve one of these problems. What I like about work problems is overall, they're fairly easy. So they usually aren't super difficult. So here is a 105-gram hockey puck, so that's going to be our mass. It's sliding across ice. The player is exerting a 4.5 Newton force, that's our F, over a distance of 0.15 meters. So that's going to be our D. And it says how much work does the player do on the puck? So I'm going to write everything that they've given me here. Now, my grams, if I'm going to use them in my formula, I'm going to need to convert them to kilograms, because we must have we've got to have kilograms in our formula. And so we want work. I'm just going to put a blank here in joules so I remember to use my units, because I don't want to do all the work of solving the problem and then not put units and then get points taken off. Okay, so work is equal to force times distance. So they actually gave us mass, but we don't need it. It doesn't hurt my feelings. I'm just going to cross it out and, be done with it. I'm not going to hold a grudge against the mass. Sometimes they do that. They'll give you stuff you don't need in a formula just to be jerks, but, we'll rise above. So force times distance, I put my force and my distance in here. When I multiply those together, I get 4725 joules. You can do 2 decimal places, 1 decimal place. I don't really care how many decimal places you go to. I'm not gonna, harp on you about sig figs. I want you to be able to do the problem. So that's more important to me, to be able to solve it. So there's your answer. So this is why I said that these are kind of easy, because there's not, a ton of different steps yet for these. So now we're going to talk about the angled one. Okay, we're going to talk that formula that had ft cosine theta. We're going to do that one. So if the force is at your right angle to your motion, your work is 0. Okay, so for example, if you're moving something horizontally, let's say that you've got a box. You've got a box here, and it's moving this way, and I'm pulling up this way, but it's not actually moving up. It's just moving this way. Your work is going to be 0, right? Because the distance you're moving up in this direction is 0. And again, work is force times distance. So if your distance is 0, if you're not moving any distance in this direction, it's going to be 0. Okay. But then you can also apply a force at an angle. And so then it's going to be this angle that's in the displacement of this direction, right? And so that's where this cosine theta comes in. So it's basically like we'll calculate, if our box is here and we're moving this way, this we'll be talking about this x component. That's what we'll be solving for. Okay. So let's do a problem and see how it goes. So here we go. I'm gonna pick a different color just because I can. A sailor pulls a boat a distance of 30 meters. Okay, that's going to be my distance. Along a dock using a rope makes a 25-degree angle. That's going to be our theta with the horizontal. How much work does the sailor do on the boat if he exerts a force of 255 newtons on the rope? Okay, so here's what we've got going on. Our force is in this direction. This is the horizontal. This is the direction which we're moving. This is where that 25 degrees is. And so then this, I guess, is our boat. Okay. Now you know why science teacher or physics teachers draw free body diagrams, because they don't have to draw pictures. You can just put little dots there. So let me write the things that I know. And again, I like to write what I know over here because I don't like to fiddle too much with all these words and things. If I'm doing math, I want to be doing math. I don't want to be reading. So here's what I know. And then here's my formula. Okay. So what I'm going to do is I'm just going to plop in these things that I know. My force is 255. My distance is 30. And then cosine 30. Okay, now if you want to enter it in the calculator all at once, instead of multiple steps, put your parentheses like this. That way you'll get it, you'll get the right answer. So we're going to get 6933.25 joules. Ooh. See, look what I forgot. I forgot my little thing here. Okay. So 6933.25, that'll be our answer. Okay. So that's how you solve that one. So far word problems aren't super difficult. I think there's some of the easier things that we do in physics. But okay, so let's now talk about energy. So we have two types of energy. We have kinetic energy and potential energy. Kinetic energy is the energy of moving, and potential energy is the energy of position. Okay, so it's involved with like not really moving. So let me try to say. So when we get to conservation of energy, we're going to have both types of energy, and we're going to have to distinguish, how much potential an object has versus how much kinetic an object has. But for now, we're going to focus on kinetic, and then we'll do potential. And then next week, we'll talk about conservation of energy. So kinetic energy is the energy of an object due to your motion, and it's measured in joules as well. So work and energy are both measured in joules. And kinetic energy, excuse me, is 1/2 mv squared. So there, your v, that v is the is where you get that motion part. Okay. The formula isn't super difficult compared to some of the ones we've done, but like when I taught physical science and the students didn't have to do things like projectiles and things like that, they didn't really like dealing with the squared. But for us, we've already used formulas that are like way more difficult than this one. So it shouldn't be super difficult for us. So here we go. Here's the same hockey puck question, right? But now they've kind of they've changed it a little bit. Okay, so let me pick another color. Okay, so let's see. We have 105 gram hockey puck. There's our mass. It's sliding across the ice. The player exerts a 4.5 Newton force. We read this before, right? Over a distance of 0.15 meters in 45 seconds. So, ooh, they've told us something else, right? We've got an extra piece of information. And then they said, what is the puck's kinetic energy? Okay, so I'm going to write what I know. My mass is 105 grams. My force is 4.50 newtons. My distance, 0.150 meters. And my time is 45 seconds. Okay, and their kinetic energy formula is Ke equals 1/2 mv squared. So we're going to need the mass this time, so we'll have to convert it to kilograms. And then we also need a velocity, so we're going to have to use this distance and time to find our velocity. Okay, so the first thing I'm going to do is I'm going to convert my mass. Okay, and I'm going to do that in a color, and then I'll do the next step in a color, and then the next step. So hopefully that kind of keeps you guys straight. Okay, so we have 1,000 grams in 1 kilogram. Okay, so that's going to give us a mass of 0.105 kilograms. Our grams to cross out. Okay, then the next thing we need to do is we need to find the velocity. Okay, so to do that, I'm going to use my V equals D over T equation. Okay, and I'm going to do my 0.150 over 45 seconds. Okay, and then I'm going to get 0.0023 meters per second. So that's going to be my velocity. And then let's see. Do like a blue color. Okay, so then the third thing we'll do is we'll actually go ahead and we're going to solve for this kinetic energy. So we've got Ke equals 1/2 times my mass, which is 0.105. I found that in step 1. And my velocity, which is 0.0023 squared. Okay, if you want to enter your this formula into the calculator all at once, I would enter it this way. Okay, that way it knows just to square this, and then your half is also in parentheses, so that doesn't screw up anything. So when you do this, you're going to get a really small number. Okay, so I got 2.77725 times 10 to the negative 7. Okay, so you could, if I was, taking a test and I was turning it in, I would do probably do 2.78 times 10 to the negative 7 joules. And I would say that was my answer. So this one was a little more difficult because we had to find the velocity and then we also had to convert the mass. But compared to some of the problems we've done in the past, it's still not nearly as difficult as some of the things we've done. I tend to like the energy unit because I feel like it's a little easier, honestly. So now we can talk about potential energy. And the reason they call it the energy of position is because we have this height right here. So it depends on how high you are. And we'll talk about that. We have something called like the reference position or the reference point that we'll talk about. So potential energy is the stored energy as a result of gravitational force between the object and Earth. And so the reference level is where we define our potential energy to be zero. And so that's also where we'll define our height to be zero. So you'll see in some of the practice problems that we're going to do that we'll kind of discuss that. We'll talk about, okay, this is where we're defining zero in this problem, and this is where we're defining zero in this problem. So that's kind of how we'll go. And you see, here we are, we're using G again. So if you memorize that, you know, you're still getting some mileage out of that, that thing that you memorized. I know I don't like to memorize stuff, so I like to know if I'm memorizing it, at least I'm like, you know, getting my so-called money's worth out of it. So let's see what we've got here. So here we've got a bowling ball. We're lifting a bowling ball. The mass is 7.3 kilograms from a storage rack, and we're holding it to our shoulder. The storage rack is 0.61 above the floor. So what I did is I called this like rack H. And then your shoulder is 1.12 meters. If I was going to do it right, write it like in a true physics fashion, I would probably do like height. I would do the H, and then I would do like shoulder. But you get the idea. And then it says when the bowling ball is at our shoulder, what is the potential energy relative to the floor? So this should kind of remind you of when we were talking about displacement or vectors. Or frame of reference, we talked about relative to the floor, relative to the train, relative to the girl, whatever. So we're kind of coming back to that type of concept. So sometimes these concepts do come back to haunt us. So here is our mass. Okay, so I'm going to do height of the rack. And I'm going to do height, shoulder, and then we're going to look for PE. Okay, so here's what we've got. We've got this person. Their shoulder is 1.2 meters from the floor, and then their the rack is 0.6 from the floor. So because we're doing potential energy relative to the floor, from the shoulder to the floor, we're going to use this full distance. Okay, this 1.2 meters. That's going to be the height we're using in this problem. Okay, because we want relative to the floor and the shoulder. Okay, so our formula is P equals mgh. And you may see in the course, I saw that they like to use Y here. I've just always used height, and honestly, it's kind of a you can't teach an old dog new tricks thing. I'm just going to keep writing that because I will not remember to put Y there just because the folks that designed this course put a Y there. 1.12, almost forgot the one. And then I'm going to multiply this together. Okay, so my shoulder relative to the floor, I'm going to get 80.1248 joules. Okay, so that's my potential energy from the shoulder to the floor. Okay, now we're going to go to another slide, and we're going to do a different one. Okay, and we're going to be relative to something else, and so our potential energy is going to be a little different. But it's okay, we'll survive. Okay, so same thing. Our bowling ball has a mass of 7.3 kilograms. The storage rack, I'm just going to call this actually like HR, so I don't have to write the whole thing. And I'm going to call this one HS because I'm being lazy because we just did this. And then it says when the bowling ball's at your shoulder, what is the potential energy relative to the rack? Okay, so now we're doing relative to the rack, not the floor. Okay, so that's going to make our potential energy different. Okay, so we have the height of the rack, and then we have the height of the shoulder, and then we're going to want the potential energy. Okay, so for this one, we want this. We want from the shoulder to the rack. So this is the height that we want. So we want 1.12. The h that we're going to use in our formula is going to be 1.12 minus 0.610 because we want this part up here. Okay, so it's going to be 0.51. So that's going to be the height that we're going to use in this problem. Okay, so you can see it's different because we're relative to something else, right? We're still the shoulder, but instead of relative to the floor, we're relative to the rack. Okay, and here's our MGH. We have 7.3 times 9.8, and then I'm going to use this this height here. Okay, and so when I solve for that, I'm going to get 36.4854 joules. So you can see it's a smaller potential energy than the last one, right? The last one was like 80 something, and now we're at 36. The reason for that is, you know, we had a much higher potential energy if we're going from shoulder, you know, from here to here, right? That's a longer distance than if you're going from here to here. Okay, so that's, you know, that's why you're going to have more potential energy in this longer line than this one because your height's bigger. Okay, and then we've got one more that I want to show you. And this one, at first you might read it and go, uh-oh, I don't know how to do that. But then if you think about it, you do. So that's why I wanted to show it to you because I wanted you to realize that they do give you the information that you need in this problem. Okay, so same thing. We've got our mass. We have the height of our rack. We have the height of our shoulder. And then it says how much work was done. So they want work by gravity as you lifted the ball from the rack to shoulder. Okay, so they want work and they want rack to shoulder. Okay, so let's write what we know. Okay. And then we'll just kind of think our way through it and we'll be okay. Okay, so let's look at our work formula. It's force times distance, okay? We've got rack to shoulder. So our distance is going to be this right here, right? Which we decided in the last slide was 0.51 meters. That's going to be our distance. So we're okay with that. But then force, they don't give us a force, okay? So let's think about that. They don't give me a force, but I'm not going to freak out. Let's see, my formula for force is mass times acceleration. Okay, they didn't give me an acceleration, but they did say how much work was done by gravity. Okay, and what is gravity? Gravity is an acceleration, right? So we could do this. Okay, and so then we can solve for this force, put this distance in, and then we can get our work. Okay, so again, I'm going to do different colors for different parts of this. That way you don't get confused and it kind of separates it. So force equals mass times gravity. My mass is 7.3 and gravity is 9.8. Right? It doesn't say we're in a space bowling alley, right? We're on Earth. So our force is 71.54 newtons. Okay, so there's my force. Now I can go ahead and I can solve for my work. So my work is force times distance. Okay, so my force is 71.54 and my distance is 0.51. So then I'm going to get 36.485 joules. Okay, so there's my work. Okay, so at first it was like, work, I don't know this, but then we just kind of think about it, right? So if you get a problem like that, especially a short answer problem on a test, and you don't really know how to solve it, or you look at it and you're like, I don't think they gave us enough. Sit back, slow down, write what you know, think it through, think about the formulas that you have. That's why I tell you guys to keep a formula sheet. That way you can go look back at some older formulas, maybe you need those. And then you can kind of just slowly work your way through it and, figure it out. So that's how you solve these work and energy problems. Next week, we'll talk about conservation of energy, which is, if you've heard of like physics roller coaster problems, things like that, those are pretty classic physics problems. Those are the kind of things you do in a conservation of energy problem. So we'll do that kind of stuff next week.